This image shows physical maps with interwoven roads and distance grid indexes. Long before we had digital data structures, we used these physical grids to calculate routes and map out the real world. Today, modern software relies on the exact same concept, translated into computer science as a graph. Mathematically, a graph is defined by the formula G equals V, E. The V stands for a set of vertices, or nodes, which represent individual objects, like a computer, a city, or a user. The E represents the edges, which are the lines forming the relationships or connections between those objects. These connections take three primary forms. In an undirected graph, the edge works in both directions equally. If we add a specific direction, it becomes a directed graph, or digraph, where node A points to node B, but not necessarily the other way around. Finally, a weighted graph assigns a specific cost, distance, or time limit to the edge itself. To analyze a specific point within these networks, we measure a vertex's degree. This is a direct count of how many edges are connected to that single node. Defining these components gives us the required vocabulary to evaluate massive, complex systems. Whether you are tracking cybersecurity attack paths or building state space searches for AI algorithms, you are relying entirely on this mathematical foundation. While a graph makes visual sense to us, a machine cannot see a web of floating nodes. We have to force these abstract relationships into the strict, linear, and physical constraints of computer memory. One method to do this is the adjacency matrix. We create a two-dimensional array representing our nodes and apply a simple binary logic. If an edge exists between two nodes, we write a 1 in that coordinate. If there is no connection, we write a 0. When mapping an undirected graph, this grid is always symmetrical. Because a connection from A to B flows both ways, you must update both the A to B coordinate and the B to A coordinate with a 1. The matrix gives us extremely fast edge lookups, but it has a major structural flaw. If your graph is sparse, meaning it has many nodes but very few connections, you are forced to store thousands of useless zeros, wasting a massive amount of memory. To solve this memory problem, we use the adjacency list. Instead of a fixed grid, we build an array where each index represents a vertex, and that index holds a dynamic list storing only its direct neighbors. In C++, we implement this using a vector of integers. To connect node 0 to node 1, we use the pushback command to append node 1 directly to node 0's vector. We allocate memory strictly when a connection actually exists. Choosing between a matrix and a list requires evaluating your specific system constraints. The adjacency matrix gives you instant edge lookups at the cost of high memory usage, while the adjacency list conserves memory but requires slower sequential searches. This architectural trade-off dictates how your final software will perform. Once the data is stored in memory, we have to navigate it. Depth-first search, or DFS, is an algorithm that aggressively explores a single path. It drives down one branch to its absolute end, and only when it hits a dead end does it backtrack to check alternative routes. To remember its previous steps, DFS relies on a stack architecture. In C++, this is naturally handled through recursion. Every step forward adds a function call to the stack, and every backtrack pops it off. There is a severe trap here. If you fail to update a Boolean visited array as you check each node, your algorithm will bounce back and forth between two connected vertices, triggering infinite recursion and immediately crashing your program. Breadth-first search, or BFS, takes the opposite approach. Instead of diving deep, it conservatively scans the immediate perimeter, checking every neighbor at the current depth before moving down to the next level. To maintain this level-by-level order, BFS uses a queue. As it discovers new neighbors, it lines them up at the back of the queue, ensuring that the closest nodes are always processed first. If you are using an adjacency list, the time complexity for both of these algorithms is O of V plus E. The maximum time it takes to search the entire graph is strictly capped by the total number of vertices and edges. Using the stack-based depth of DFS gives us efficient pathfinding, while the queue-based breadth of BFS guarantees the shortest path. Mastering these structures allows you to engineer complex routing protocols, global search engines, and the data analytics that power the modern web.